Welcome. We're going to cover what it takes to get a tailwheel endorsement. We will also touch on the basics of attitude flying and the characteristics of tailwheel aircraft. A long time ago, everyone learned to fly in a tailwheel aircraft.
The modern airplane is well designed. Structurally, it is light and flexible and very strong. All aircraft wings are fundamentally the same shape. This shape is the basic airfoil. The tail assembly is checked. Once the student is acquainted with the outside of the airplane, instruction inside begins. He sits in the pilot seat, the instructor on his right. When he knows how to use the brakes and start the airplane, he is taught to taxi the airplane on the ground. He is taught ground courtesies and how to watch for other aircraft.
There have been many changes in flying since that time. All pilots must have a tailwheel endorsement by an authorized instructor to act as pilot in command of a tailwheel aircraft, unless the pilot had pilot in command time prior to April 15, 1991. The 90-day currency to carry passengers in a tailwheel aircraft must be done in a tailwheel aircraft, and all the landings have to be made to a full stop. We often use Newton's second law of motion to explain. We've all pushed a car, or most of us have, and when the car is stationary and you start to push, it takes a lot of effort to get it to move. Once it starts moving, it's not quite as much effort. You can go. If you put the same amount of force that you had to get it moving continuously, you would have to run, and you would go faster and faster and faster. Eventually you couldn't run fast enough to keep that much force on it. Now, if you wanted to stop, when you first started, you could just release your pressure and it would probably stop. After it got going fast, then it would just keep going until you ran around in the front and started pushing the other way to make it stop. Immediate correction of the rudder is required. Right rudder, then you're going to need left rudder, and then right rudder again to keep the nose pointed right down the middle. Let's see the forces acting upon the aircraft in a crosswind, be it tricycle gear versus the tail wheel. The tricycle aircraft's center of gravity is in front of the main gear, giving it positive stability. The tailwheel aircraft center of gravity is behind the main gear, causing the aircraft to have negative stability. The gorilla effect. The force required by the rudder to correct turning increases with time and the radius of turn. If the turn is not stopped quickly, the rudder will not have enough force to correct turning. Under power, the rotating slipstream wants to make the aircraft turn to the left. The asymmetric loading of the propeller, or P effect, causes the aircraft to turn left, more so when the tail is on the ground. Gyroscopic precession of the propeller causes a turning motion when the tail comes up. All of these effects have to be corrected by the rudder control quickly, or Newton's law will increase the turn, resulting in loss of control. The tetrahedron and wind T show the direction of the wind, but are often tied down to show runway in use. The windsock shows the wind direction and wind speed. It is the most reliable source to determine what action to take to compensate for the wind. Aircraft characteristics. The landing gear geometry. The tread, which is a distance between the wheels. The distance from main to the tail wheel. The relationship to the center of gravity. The Luscombe has a narrow tread. The Swift has a very wide tread. The Cessna 190-195 has a very long distance between the mains and the tail wheel. The Storch aircraft has a very, very high center of gravity. The tail gear geometry. Some tail wheel has a full swivel. Most are steerable, some are not. There's a lockable tail wheel. Could have just a skid. And the size of the tail wheel. Weather vaning tendency. The tendency for the aircraft to turn into the wind. Depends on the vertical fin size, fuselage area, the brakes, and the rudder effectiveness. The Stinson has a large vertical stabilizer and a large fuselage area. The Malanka has a very, very small rudder. Visibility. In some aircraft, such as a backseat of a biplane or a Cessna 195, you cannot see over the engine cowling. You want to make S turns while taxiing, taxi at a slow speed, be aware of the tail during all turns. Eternal vigilance is necessary. The runway surface is very important. Normally we use paved runways. In winter, ice and snow may cover the runway. The best runway for a tailwheel operation is a grass runway. Some operations require that the plane be landed on whatever surface is available. Operations are very important. Before starting the engine, make sure that the stick is back so the elevator is up to keep the tail on the ground. Before taxiing, do a brake check. When taxiing into the wind, remember climb into the wind, stick back and towards the wind. When taxiing downwind, remember stick forward and opposite the wind. Dive away from the wind. On a turn to downwind, move the controls from climbing into the wind to diving away from the wind. If the wind is very hard, it may be difficult to turn downwind because of the wind on the rudder keeping the airplane from turning. In that case, you may turn into the wind and do a 270, and the momentum will carry you on around to downwind. Turning upwind is very easy because the wind helps the aircraft turn. Just remember to go from diving away from the wind to climbing into the wind. To take off, keep the stick back, roll down the center line, lift the tail by putting the stick forward, take off, roll with the tail up, and then back on the stick for fly off. Oops, it didn't go down the center line. Remember all torque factors: rotating slipstream, the P factor, the gyroscopic moment of the propeller. They all needed to be corrected by the rudder. Apply power, stick back, look ahead at a point on the horizon. The rotating slipstream and the P effect will cause the nose to turn to the left. Correct with right rudder. Newton's law of motion will cause the nose to go right if you do not apply left rudder to stop the turn, then right, then left. Apply forward pressure on the stick to raise the tail. Look ahead. Changes in torque, gyroscopic precession, and P effect will change the direction of the nose. Correct with the rudder. Roll on the mains. When Airspeed approaches liftoff speed. Apply back pressure slowly and smoothly. Do not look at the airspeed indicator, just glance and return looking out the windscreen. Attitude flying. Not the pilot, the airplane. Pitch attitude can be determined by looking at the bottom of the wing relative to the horizon. Pitch attitude can also be determined by seeing how far the nose is above or below the horizon. To determine the aircraft is level, look out at the wingtip, left and right, and if both are the same distance above the horizon, the aircraft is level. Bank angle can be determined by reference to the horizon looking straight ahead. When banking, the new pilot has a tendency to lean from one side to the other to make himself perpendicular to the horizon. You should not do that. The pilot should remain straight in the seat. The G-forces will automatically allow that to happen. Flying by the seat of your pants. Today's meaning, is to decide a course of action as you go along rather than a predetermined plan or mechanical aids. This is an early aviation phrase. Aircraft initially had few navigation aids and flying was accomplished by means of the pilot's judgment. The term emerged in the 1930s and was first widely used in reports of Douglas Corrigan's flight from the USA to Ireland in 1938. That flight was reported in many U.S. newspapers of the day, titled, "Corrigan Flies by the Seat of His Pants." Today, we are including forces on your buttocks when slipping or skidding. Step on the ball is a common phrase. In attitude flying, it would be apply rudder on the side of the force that you feel on the seat of your pants. A good approach makes for a good landing. Use best glide speed to beam touchdown point with power reduced for rate of descent required. Maintain best glide speed with trim and descent rate of power. On short final, maintain minimum descent rate speed. Minimum descent rate speed is halfway between best glide speed and stall speed, approximately 1.3 times stall speed. A good pattern results in a good landing. This is a truism. The right altitude and spacing downwind leads to turning a proper base leg. The turn to final will be unhurried and rolling out exactly on center line of the runway. With proper airspeed and attitude, the final approach to touchdown will be without distraction. Proper spacing from the runway at pattern altitude is when the runway is at a 45-degree angle or halfway down the strut as seen by the pilot. While turning final, adjust the turn to roll out on the center line of the runway. The far end of the runway should appear to be directly over the approach end of the runway. The touchdown point with the present attitude and power setting will be the spot where there is no movement relative to the windscreen. The approach is the same as a tricycle gear aircraft. Flare out close to the ground, a foot or two. Keep flying as long as possible, bringing the stick back and attempting to keep the airplane in the air. When airplane stalls, it will land on all three wheels and must be guided straight with the rudders.
During a stabilized final approach, the angle of attack determines the descent angle at a constant power setting. If the angle of attack is increased, causing more drag, the descent angle increases, landing shorter. If the angle of attack is decreased by lowering the nose, there is less drag and higher airspeed, landing further down the runway. Three-point landing glide until you're about a foot off of the ground. Keep coming back on the stick, trying to keep the airplane from landing. And when it does touch down, it'll touch down in a three-point attitude. If the main gear touches first, the downward momentum will cause the tail to go down, increasing the angle of attack, causing the airplane to go back into the air, which is referred to as a bounced landing. To recover from a bounce landing, the best way is to add full throttle and go around. The other option is to let the plane descend and flare again when close to the ground. If you're too slow, you may have to add power to prevent a hard landing. Landing tailwheel first causes the nose to drop rapidly on impact, decreasing the angle of attack, and it will probably stay on the ground. Why make a wheel landing? Maximum controllability of airplane through touchdown, reduce risk of being blown about by wind gust, improve visibility during landing run, ability to set airplane on ground at any speed, safety at night when overloaded or icing. Wheel landings are hard to learn. Why is that? They are the exact opposite of a three-point landing. They are not fully understood. Pilots fear hitting the prop when applying forward pressure. Forward stick the moment the wheels touch and use that rudder to keep it going straight. On most aircraft, the prop will not hit the ground if the wheels are on the ground. Make the approach the same as you would making a three-point landing. Flare out close to the ground, a foot or two, with a minimum descent rate which may require a little bit of power. Don't try to get the wheels on the ground, just fly along the runway until the wheels touch. Apply forward stick immediately, ease off the power, hold the elevator till it lowers, and keep it straight with a rudder. Once the tail is lowered, apply back pressure. A short field landing is the same as a three-point. Stick full back after landing, pump the brakes. A soft field landing is the same as a three-point. Stick full back after landing, no brakes. Crosswind landings and takeoffs contribute to a large number of general aviation accidents each year. Newer aircraft have a demonstrated crosswind component that shows what a test pilot has been able to do. A rule of thumb is a safe crosswind component is equal to 20% of the stall speed. You should establish personal minimums not to exceed the demonstrated crosswind component. You should not exceed a crosswind that you have not recently done satisfactorily. The objective of crosswind landing is to simultaneously keep the airplane's ground track and longitudinal axes aligned with the runway center line throughout the final process. Crosswind component is not shown on METAR, given on ADAS, or by the tower operator. It has to be computed. Crosswind component is equal to the sine of the angle of the wind times the wind speed. The crosswind component can be computed using a sine table, but a rule of thumb, 30 degrees is equal to 50% of the wind speed, 45 degrees is equal to 70%, and 60 degrees 90%. Using the crosswind component diagram, you can easily find the crosswind component for any wind speed and any wind angle. Also give you the headwind component. Before takeoff, get the wind speed and direction to determine the crosswind component. The windsock is the best way to get the wind speed and direction to determine the crosswind component. You do not want to be using a calculator and looking at diagrams while approaching an airport. You want to be looking for traffic. ATIS or the tower will give you the wind direction and speed. Remembering the rule of thumb for crosswinds. If the wind is 30 degrees or less from the runway heading and the wind speed is less than 20 knots, it's okay. If there is no ATIS or tower, make a normal approach to the active runway, but plan to overfly the runway at about 20 feet. The crosswind component will equal the correction angle if you fly at 60 knots or 70 miles per hour. If the crab angle is 18 degrees, the crosswind component is 18 knots, probably too much for a landing. Final, line up with the center line, crab to keep in the center line. On short final, slip into the wind, keep fuselage straight, touch down while slipping. Ailerons used to keep the aircraft in the center line, the rudder used to keep the aircraft straight down the runway. Keep the windward wing down as long as possible to prevent sideways motion and perform the landing as any other. If a stall landing, a three-pointer was intended, it is still performed as a stall landing, although it will be a two-pointer. If a wheel landing was intended, the first contact with the runway will be on a single main wheel. If you determine the crosswind component is more than you have practiced, go to another airport with the runway into the wind. Waiting somewhere is better than damaging your aircraft. The requirements for tailwheel endorsement are stated in FAR 61.31. Ground training should include the aircraft systems and speeds, torque sources and their controls, positioning of the controls when taxiing, normal takeoffs and three-point landings, wheel landings, crosswind takeoff and landings, recovery from a bounce and go-around. The tailwheel endorsement flying portion in Block 1 would include taxiing, normal takeoff, and air work including turn, stall, slow flight, simulated pattern, and ground reference maneuvers. In Block 2 would be normal takeoffs and landings, speed control, bounce recovery. Block 3 would include three-point crosswind takeoffs and landings. Block 4 would be wheel landings. Block 5 would be crosswinds greater than 5 knots and crosswind wheel landings. The amount of time to complete the tailwheel endorsement would be dependent upon the pilot's experience and the aircraft that he has flown, the winds during the training, how much the pilot studies tailwheel flying publications, and the model of aircraft. 7 to 15 hours should be expected. We recommend that you participate in the FAA Safety Team Wings program. Go online at www.faasafety.gov. Sign in if you're already registered, or create an account if you are not. Promote safety in aviation. Participate in the Wings program. Thank you. Let's go fly.